Module 1, Lessons 1 and 2, Construct an Equilateral Triangle. We're going to start this lesson off with some vocabulary here. We are going to be doing a lot of geometric constructions in this module, and a construction is simply a set of instructions for drawing points, lines, circles, and figures in the plane. A geometric figure is simply a set of points that are in the plane. Now, you have probably drawn things like a triangle in the plane, and you use the vertices to draw that triangle. What you need to start thinking about is it's not just these 3 points, we'll call them points A, B, and C, but it's also all of these infinite number of points that make up the segments as well. An equilateral triangle is a triangle with all sides that are congruent. And what does congruent mean? Equal length. And the name tells us exactly what it is here. Equal sides. Equilateral means equal sides. Collinear, we saw this in the last lesson, remember, together on a line. That's 3 or more points that lie on the same line. Also in the last lesson, we saw length of a segment. So the length of segment AB, remember our notation there says segment, is the distance. We said length is a distance from point A to point B. And we use this notation for length. This says the distance from point A to point B, the length of AB. And so in this book, length AB can also be denoted as distance from point A to point B. So remember that notation as well. Next here is a very important vocabulary word. A regular polygon is a polygon that is both equilateral, so equal sides, and equiangular, equal angles. Notice here on our diagram, all of the sides are marked congruent and all of the angles are marked congruent. So regular polygons are going to be very important to us. Our first formal definition is the definition of congruence. Remember our symbol here. Congruence means if they are congruent, they are the same. And in math, that means equal. If we are talking about segments, congruent segments have equal length. If we are talking about angles, congruent angles have equal measure. Segments have length, angles have measure. So that's our vocabulary. Now it is time to introduce definitions, postulates, and theorems. This is what makes geometry geometry. A postulate, also called an axiom, is an accepted statement of fact. Postulates are accepted as fact. These are the basic building blocks for our logical system. They're going to allow us to do proofs. A theorem, which will be introduced later, is a conjecture, and a conjecture is an if-then statement. If this is true, then you can say this happens, and we will get to those. Theorems are proven, and they were proven using our definitions and postulates. And postulates and theorems are going to be very useful to us when we do our proofs. So let's look at some postulates here. Our first postulate says through any 2 points, there is exactly 1 line. And you were introduced to this in algebra. And we're given 2 points. You could plot 2 points, whether it's the y-intercept and slope or just 2 points, and then draw a line through them. Line T passes through points A and B, and it is the only line that will pass through those 2 points. It's very straightforward. Next, if 2 lines intersect, they intersect in exactly 1 point. So 2 lines will only ever intersect in 1 point. This is also very straightforward, but also very important. So we can say lines AE and line DB intersect at point C. The next one is possibly not as intuitive as the other ones are, but when we think about it here, it'll be okay. 2 planes intersect. When they intersect in exactly 1 line. Now, you might think you're going to have some trouble with this, but I told you to think about geometry, think about the world around you as this 3-dimensional set of an infinite number of points. And take a look at the wall. And the wall is just part of a plane. The plane that the wall is in goes on forever. Where our 2 walls come together here, they come together in a segment because we're just talking about parts of a plane. But the 2 walls come together in the corner here, which is just part of this line. And you have this line, another line, where the wall and the ceiling intersect, and where the wall and the floor intersect. So this one's not as hard as you think it's going to be. This is happening in the world around you. Next, we have through any 3 non-collinear points. And what does non-collinear mean? This means not together on a line. Right? Collinear was together on a line. Non-collinear, not together on a line. There is exactly 1 plane. So if we look at our plane over here, we have 3 points, points Q, R, and S. And those 3 points, there can be one and only one plane that contains all 3 of those points. And I like to think of this as a camera tripod. So you put your camera on these points to keep it upright. Now what if you want to put your camera on a hill? Well, you're going to have your camera going like this. And these 3 points, there's going to be one and only one plane that is going to contain all 3 of those points. And this plane is going to be sloped like the side of a hill. Plane P is the only plane that is going to contain these points Q, R, and S. That one's a little harder, but if you start looking in the real world, you will see this. Our last postulate here is actually named. When we do proofs, if the postulates and theorems are not named, you have to write them out. Some of them have names, and you can just use the name. The ruler postulate is very powerful. It says every point on a line can be paired with a real number. So we are just taking a line and turning it into a number line. So if we have point A here and we say it's at -3, and then we go -1, -2, -1, 0, 1, 2, 3, 4, 5, 6. We'll put B at 7. How's that? So I've now paired up my points with numbers. Just turn this into a number line. What the ruler postulate allows us to do is to find the distance between these 2 points is the absolute value of the difference of the coordinates. And what does difference mean? Difference means subtraction. We are going to minus those. This will give us the length of segment AB. So we have a formula here. The length of AB, remember that's how that's read, is the absolute value of the value of coordinate A minus the value of coordinate B. So let's take a look at this. If I do the absolute value of -3 minus 7, What do I get? I get negative 10. Absolute value makes that positive. That segment from A to B is 10 units long. Well, what if we go the other direction? Because we said we could name segments either direction. Well, we would take 7 minus a negative 3, and minus a negative is just plus a positive. That would give us 10. Absolute value of positive 10 is still positive. This is because distance is always a positive measurement. If we start here at negative 3 and count our way that way, it takes us 3 units to get to 0, and then 7 more to get up to 7. So that's 10. 3 plus 7 is 10. If we count this direction, it's 7 to get down to 0, and 3 more places to get to negative 3. Because we're counting distance, it's always positive. The absolute value lets us count any direction on our number line. Lets us find a distance, any direction on our number line. So those are our postulates. Lots of good stuff there. Now we need to do some review of circles. A circle is a set of all points that are equidistant from a point called the center. So if we look over here at our diagram, there is the center of our circle, and our circle is made up of all points in all directions here, all the way around, that are equidistant from that point in the center. We name a circle by its center using this circle symbol. So this would be named circle P. Now, how do we get all of those points that are equidistant? We use the radius. And a radius is simply a segment that has one endpoint at the center and the other endpoint is on the circle. So we put our point at the center and we draw a segment to the circle. And so segment PC is the radius. And segment PC, that distance, the length of that segment, is the length that we use to find all of these other points. So we could draw radii. We name a circle by its center using this circle symbol. So this would be named circle P. Now, how do we get all of those points that are equidistant? We use the radius. And a radius is simply a segment that has one endpoint at the center and the other endpoint is on the circle. So we put our point at the center and we draw a segment to the circle. And so segment PC is the radius. And segment PC, that distance, the length of that segment, is the length that we use to find all of these other points. So we could draw radii anywhere. And there's an infinite number of radii around this circle, and they are all the same length. They are all going to be congruent. All radii within a circle are congruent. A diameter is a segment that contains the center of the circle and has both endpoints on the circle. So a diameter passes through the center. And there are an infinite number of diameters on our circle as well. They will all pass through the center. If you don't pass through the center, you're not a diameter. You're a chord, but that's information for later. And a diameter is just two radii that form a straight line. Congruent circles, this is important information here, have congruent radii. We've already said that all radii within a circle are congruent. And if you have congruent circles, which means they are the same, they are equal, all of their radii are going to be congruent. And a central angle is an angle whose vertex is the center of the circle. Thus, central angle. So if we look at angle APC here, we have a central angle. Angle APC is a central angle. Some more parts of a circle that we will use as we go in our lessons here. An arc is part of a circle. Just like a segment is part of a line, an arc is part of a circle. One type of arc that you probably know is a semicircle, which is half of a circle. We have two other types of arcs. First one is a minor arc, and a minor arc is smaller than a semicircle. You name the minor arc by its endpoints. So over here, from R to S is a minor arc, and notice our notation is an arc, just like segment, only this one's curvy. We could also name this arc SR. Just like segments, they could be named either direction. The other type of arc is a major arc, and a major arc is larger than a semicircle. We name a major arc or a semicircle by its endpoints and another point on the arc. So our major arc here also goes from S to R, but this time we're going the long way. So we need to denote which direction we're going, and because it's a major arc, we say that we are going from S to R, but this time we're going through point T. So if you're naming a major arc or a semicircle, make sure you use 3 letters when you name your arc. Our last part here is going to be looking at Euclid's Proposition 1, and this is work that we will be doing in class, and I'm just going to go over it quickly here. And Euclid's Proposition 1 was to construct an equilateral triangle on a given finite line. So let's break this down. Construct means we're going to use our compass and straight edge. Equilateral means we've got equal sides. We want an equilateral triangle on a given finite line. Finite means that there's an end to it. So we're looking at a segment. So he said, let's take segment AB. And I want to construct an equilateral triangle, which means all of the sides are going to have this given length AB. And what he did was he said, let's take our circle BCD, that's this one right here, and say that it has center A. So I'm going to draw that circle down here. Here's our circle with center A, and we know that it has radius length AB. He said, and then take circle ACE. So that's this circle right here. And it has center B. So I'm going to draw that circle right here. So there's circle B. And we know it has radius BA, of length BA. Now look what we have here. We have radius segment AB, and we have segment BA. What did we learn in the last lesson? Those two are the same segment, aren't they? So we can say that they are congruent. And if our segments are congruent, we can say that they have the same length. Now, how is this going to help us draw an equilateral triangle? Well, let's think about this. Segment AB is the radius of circle A. That means I can draw another radius right here, radius AC, and what do I know about AB and AC? They are congruent. So he says that here. The length of AC is equal to the length of AB. And I can go to circle B. And I can draw another radius, radius BC. And what do I know about circle B here? The radius BA is congruent to radius BC. Length BC is equal to length BA. And I have congruent circles because they have congruent radii. I used segment AB as my radius for both circles. So let's go back up to our diagram here. We have green circle with radius AB and radius AC. We have blue circle with radius BA and radius BC. And what do I know about all of these radii? They're congruent. And if all of those lengths are congruent, then the triangle they form is an equilateral triangle. So we used our compass to measure the length that we wanted, and as we drew our circles, we knew that the points on that circle are all going to be the length that we want for the side of our triangle. And where our circles intersected here was the point where our sides would intersect. And if you notice, there's another intersection point down here. What could we say about that triangle? Yep, that's right. It's another equilateral triangle. So circles are very useful and very cool.